Welcome back, everybody. Let's talk about LeChatelier's principle. LeChatelier's principle states that if you have a system at equilibrium and an external stress is applied to that system, you are going to have the chemical system adjust in order to offset the stress, and it will reach a new equilibrium. And you can have that external stress take a variety of forms. It might be changing concentration of one of your chemicals. It might be changing the volume of a system for a gas that it's in. It might be changing the temperature of the system. All of these things are going to impact your equilibrium. Let's start by looking at how changing concentration will impact your equilibrium. So this is the reaction we did in lab earlier this week, where we have iron and thiocyanate reacting to form iron thiocyanate. And for that reaction, Kc is 113 at 20 degrees Celsius. So let's investigate what changing concentration does. If we have the reaction between iron 3 plus ion and a thiocyanate ion to form iron thiocyanate, I know that the equilibrium constant for this reaction is 113 if I'm at 20 degrees Celsius. What would happen if I were to add some additional thiocyanate? In order to answer this, we really need to look at our reaction quotient. So for this reaction, the reaction quotient would have the iron thiocyanate complex ion on top and iron and thiocyanate in the denominator. So if I add additional thiocyanate, this value right here is going to increase. That's in the denominator. It makes Q too small. So in order to reestablish the ratio needed at equilibrium, as seen in that equilibrium constant, I'm going to have to use up some of those reactants and form additional products in order to make the denominator smaller and the numerator larger to get back to that value. And so we say that this reaction will proceed toward the products. What if instead I were to remove some iron 3 plus? Again, we have to look at our reaction quotient. But now the concentration of the iron ion is decreased. And so that means that Q is going to be too large. Q is going to end up being larger than the equilibrium constant. And so in order to reestablish equilibrium, some of the products are going to need to form reactants. And so this will proceed toward the reactants. Let's take a look at one final example with changing concentration. So here I have the reaction between nitrogen and hydrogen to form ammonia, and I know Kc is 2.37 times 10 to the negative third when I'm at 720 degrees Celsius. So at equilibrium, we have a set ratio of reactants and products, and it turns out that these concentrations were 0.683, in this instance 8.8 and 1.05 for the ammonia. If instead of having 1.05 molar as the concentration for the ammonia, if that were to be increased by simply adding ammonia, so that the new concentration was 3.65, what's that going to do to the equilibrium? Again, come back to your reaction quotient. What I've done here now is I've increased the concentration of ammonia. So Q is going to be greater than K. I have too many products. And so in order to reestablish equilibrium, I'm going to have products form additional reactants. And so this reaction will proceed toward the reactants. Changing the volume or the pressure of a gas is really the same argument as changing concentration. If you have a gas that is in a container, and you take that same gas and put it into a smaller container, typically by just crushing the container, you'll notice that the concentration of gas is higher. So that molarity, that moles per liter, would have increased. And as a result, the same kinds of arguments that govern which direction a reaction will proceed when you change equilibrium due to changes in concentrations are going to apply here. So what would be the effect of decreasing the volume on each of these three reactions? So again, remember, if you decrease the volume that a gas is in, you're going to increase the concentration. And you would also, if you're working with a Kp value, be increasing the pressure. Those particles would be in a smaller container and they'd be hitting the walls of the container more often. And just like before, where I said, let's come back to our reaction quotient, we need to come back to the reaction quotient expression here as well. Okay, so here's my reaction quotient, and we can see that there were two solids, so they're not in the reaction quotient at all. I have two different gases. If I decrease volume and therefore increase the concentration of the pressure, I'm going to affect both of these gases. But since the concentration of oxygen is cubed, the effect will be greater in the denominator. And so my denominator is going to increase more than my numerator will because there are more moles of gas and therefore that concentration or pressure is going to be cubed. So since the denominator is what's going to get bigger more rapidly than the numerator is, this is going to give me a Q value that is less than K. Remember, it's products over reactants. So this means that I need to have some of the reactants form products in order to reestablish and get back to that original value for K. And so this will proceed toward products. The second example, if we take a look at its reaction quotient, if the volume decreases, and so the pressure of all the gases or the concentration of all the gases increase, then the denominator will be impacted, but the numerator will be impacted more because there are 2 moles of gas and 2 different gases involved there. And so that means the numerator would get larger and Q will be greater than K. And so as a result, to reestablish equilibrium, you're going to have some of those products become reactants. And so the reaction will proceed toward the reactants. The bottom example here, if we look at its reaction quotient, there's equal moles of gas on the reactant and the product side. So any change in volume will affect the concentration or affect the pressure equally in the denominator and in the numerator. And so Q is still going to be equal to K. And so there'll be no effect for changing the volume or effectively, therefore, the concentration and the pressure of these gases. One important thing I want to point out is that this conversation about changing the volume and affecting the concentration and the pressure really applies to gases. Solids and liquids aren't in your equilibrium constant expression in the first place, and aqueous solutions have a set volume, so you can't change their volume readily. Let's take a look now about how changing temperature is going to impact our equilibrium constant. This is different. In both of the other 2 examples we've looked at, changing concentration or changing the volume of a gas system, really what you're doing is trying to reestablish your value for K. You want to get back to that equilibrium ratio. If you change the temperature, you will change the value for K. This is the only way for a particular chemical reaction that we can change the value of that equilibrium constant. All the other changes, you're just trying to get back to where you were before. This one, you actually have a new target. Okay, so let's take a look at the reaction down below. So I've got dinitrogen tetroxide reacting to form nitrogen dioxide. This is an endothermic reaction. And if we're changing temperature, it makes sense that this relates to the change in enthalpy because we know that's the heat of a reaction. So let's draw a reaction coordinate diagram where the reaction progress is on the x-axis and the enthalpy or energy is on the y-axis. If I look at this first reaction, delta H for the reaction is 57.2. So I know if I look at my reactants and my products, that my products have a higher enthalpy. And if I look at how the energy changes along the way, there's always a little hill. That represents your activation barrier, your activation energy for the reaction. If I were to change the temperature, let's try to increase the temperature. Let's think about what impact that's going to have on the reaction that's happening. The energy for the reactants to turn into products, so the activation energy for the forward reaction, was pretty high. There was a pretty tall hill to overcome for the reactants to turn into products. For the products to turn into reactants, so EA of the reverse reaction, it was already a much easier prospect. So if I increase the temperature, this is going to have a greater impact on the rate of the forward reaction. The rate of the forward reaction is going to increase significantly because far more of the collisions are going to be successful. Well, if the rate of the forward reaction increases, then I'm going to make more products. And if I make more products, my value for K is going to increase. And if the value for K increases, what we're going to see is that the reaction will proceed toward the product side. And then once we have reached this new equilibrium value for K, the reaction will again come to equilibrium and the rate of the forward and the reverse reaction will be equal. I'm just going to have more of the products formed. On the contrary, if I take a look at the reaction down below, and make the same kind of diagram, I see that this is an exothermic reaction. Again, there's going to be an activation energy barrier that will have to be overcome. And for the forward reaction, that's relatively low. But for the reverse reaction, that activation energy barrier is pretty high. So if I were to increase the temperature, then the rate of the reverse reaction would be impacted more, because now many more of my collisions are going to have enough energy to occur, which means I'm going to form more reactants, and K will decrease. And so what we're going to observe is that the reaction will proceed toward the reactant side as it goes to establish that new equilibrium. Let's take a look at the effect of decreasing the temperature. So back up on this upper reaction here, if I were to decrease the temperature, it's going to be much, much harder for the reactants to make it over that hill. They won't have enough energy. So you'll have more reactants collecting. And that means that your K value is going to decrease. And so what you will observe is that the reaction will proceed toward the reactant side until that new K is established, until you reach that new equilibrium that happens to have a smaller ratio of products to reactants. On the lower exothermic equation, now if the temperature decreases, it's the reverse reaction that is impacted more. So very few of my products are going to be able to form reactants. So if we decrease the temperature, I'm going to get more products, and so K will increase, and we would observe that the reaction would proceed toward the products. And again, once you reach that new ratio, then the reaction would be at equilibrium and the concentrations would stop changing. The fact that the value of K depends upon the temperature actually gives us a really nice way to relate equilibrium constants to the enthalpy of a reaction. And the mathematical relationship that does this is called the Hoff Equation. And so the Hoff Equation says that the natural log of the ratio between the equilibrium constant at two different temperatures is equal to the enthalpy of reaction divided by the ideal gas constant. But this ideal gas constant is in terms of energy, so it is the same number, just with different units. It's going to have a different apparent value. And this is 8.31 joules per mole Kelvin. And then multiplied by the difference between 1 over T1 and 1 over T2. What we can do with this equation, if I know the equilibrium constant at two different temperatures, I can solve for delta H. If I know the value for delta H and one equilibrium constant, I can solve for an equilibrium constant at a different temperature. Or I could figure out if I know both equilibrium constants and delta H, I can find what temperature a particular reaction is occurring at. We'll work more with this in class because I want to be with you while we work through natural logs for the first time. We just understand that this is a relationship that can be very useful to help us learn more about a reaction. Last thing I need to talk about when it comes to LeChatelier's, what does the effect of a catalyst have? And it turns out a catalyst has no effect on the position of an equilibrium. A catalyst will lower the activation energy for both the forward and the reverse reaction equally. And so as a result, both processes will speed up, but they'll speed up in equal amount. And so there's no net gain toward products or toward reactants.